Okay, we're live. Hi, this is the precision time control optimization using genetic algorithm talk. The three authors and speakers are right there, Maciej, Milena, and Marta. I am now, thank you for the applause. Thank you. And now I'm just gonna start playing the video and we'll hide the speakers. And at the end of the video, we'll bring them back in for the Q&A. Okay, thank you.
Okay, hello. I'm Maciej Machnikowski, and together with Marta A Plantykow and Milena Olech, we'd like to present the results of the proof of concept work that we did, and we used the genetic algorithm to optimize time synchronization of PTP. The growth of LTE and 5G deployments puts stricter timing requirements, and we started looking at the last mile of it to see if we can easily optimize the synchronization process done by tools from the Linux PTP project. At this stage, we actually focused on the synchronization of system time to the PTP time using PHC2sys. So without further ado, let's move on. And let's start with an agenda. I'll briefly introduce it. At the beginning, we will introduce basics of PTP, briefly go over how the PTP stack works to synchronize the time in our system. Then we will talk a little bit about the PID controller that's used to control the objects and is used widely in the Linux PTP project. Then we will introduce genetic algorithms, present the data evaluation methods that we chose to use for scoring the results of each of the run. And then we will move on to the practical side of the POC, starting with the framework that we developed to gather the data and process it, present the results, and finally talk about the future work and brief summary. So let's start with the PTP stack, how the PTP on Linux works on Linux. Let's start at the bottom in the hardware level. So this is our network adapter. In it, we obviously have the queues that are used for transmitting the packets. But also, if we enable the network adapter to actually do the PTP acceleration, we usually put the PTP hardware clock inside it. And this is the clock that is actually synchronized in the process of the 1588 protocol and is used to generate the hardware timestamps. So in the upper layer, obviously we talk to this device both to the PTP hardware clock and to the queues via the PCI interface. And in the kernel of the Linux, we run the NIC driver that is exposing the interface to the stack that is responsible for passing along the timestamps. And we also expose the separate PTP clock character device, which can be used to control the PHC that's inside our NIC. And at the top of it, there is a user space with the Linux PTP project. And the Linux PTP project uses standard kernel interfaces, so it interacts with the network stack using the sockets and socket options to configure the timestamping. And it uses the IOCTLs to the PTP clock character device that resides under the dev PTP subsystem. And in the end, there is a system clock shown at the top of it in the user space. It obviously is a piece that resides in the kernel space, but here it's drawn in the user space because there are special CPU instructions that can read the system timer very quickly from any user space application. Now we will introduce briefly the Linux PTP project. As I mentioned before, it's a set of user space tools that can be used to maintain, to synchronize the time and maintain the time synchronization on our system. Among others, it implements the 1588 PTP functionality, and it uses standard kernel interfaces to synchronize and manage the time inside the PHC and all other clocks. And it supports both hardware and software timestamping. And obviously, you will get better synchronization results while using hardware accelerated timestamping. So like we said before, it starts with the NIC that has the PHC inside it. And the first tool that we will run to actually synchronize to the grandmaster that's in the network is the PTP4L. This tool will implement and follow the 1588 protocol. So it will receive and it will get the transmit and receive timestamps from our network adapter. And then it will control the frequency and phase and time inside the PHC. And if we want to use the time throughout our system, the best way is to read it from the system clock. So the first thing we need to do to transfer the time is to transfer the time to the system clock from the PHC. To do that, we will use the PHC to sys tool. So this tool will run the special IOCTL operations to measure the offset between the system clock and our PHC clock. And then we'll adjust the frequency of the system clock to match the frequency of the PHC. So now, Marta.
So as Maciej previously stated, PTP implementation in Linux uses a PA controller. And a PA controller is just a specific type of a PID controller where PID stands for proportional, integral, and derivative. Such controllers were designed for systems that require continuously modulated control, and they are mostly widely used in a systems that require continuous control. And besides that, those systems, they use the idea of the feedback loop. And to make it clear, feedback loop is just simply a part of a system in which some portion of the output is used as an input for the future behavior. In this case, the system's output signal that is handed over to the input in a feedback loop is used to calculate the error signal. It is equal to the difference between the set value and the computed value. This variable is needed as the error signal is used to control the object. And I will present the example PID control block diagram in the next slide. And I will explain more precisely how everything works once we get there. So the quality of a control system that is based on this technique depends, of course, among others, on the PID controller parameters. And there are many possible PID algorithm implementations, but in this case, we'll focus on, let's say, the most popular one, in which there are three parameters, namely KP, KI, and KD. The first of them that is called KP, or in other words, it can be called a proportional term. It multiplies the error signal by the number that is assigned to the KP. It means that it responds immediately to the current error value. The integral term, KI, multiplies the integral of an error by KI, or in other words, it sums error over a time. And the last part, which is in fact not used in our case, it is a derivative response described by the parameter K2. It is proportional to the rate of change of the process variable. So in the case of Linux PTP implementation, we are dealing with a PL controller. So you can easily say that the value that is assigned to the KD equals 0. And now we can take a look at the PID block diagram. So on this slide, we can see not only a PID controller, but as a whole a control system. And such system usually consists of a controller, which, as I previously explained, is a combination of the three basic building blocks: the proportional, that is placed at the top, integral, that is located in the middle, and differentiator, so the bottom one. Besides the controller, the other part of a control system is a process that is usually described by a transfer function. A transfer function represents how the process input signal transfers into the output signal. So, for example, we can refer to the voltage and the room temperature when thinking about the air conditioning. And last but not least, there is also a sensor. So in an ideal world, the sensor is, let's say, transparent to the whole control system. It means that its transfer function can be omitted in the calculations as it equals 1. But in real life, sensors can introduce another transfer function that should be considered when modeling the whole process. Simply saying, for example, that they can introduce a delay. The system is also described by a set of signals such as R, E, U, and Y. And the input signal that is marked on the slide as R of t represents the value that the control system is aiming to reach. So taking into account the previously described example, we can say that it will be, let's say, 21 degrees. The response of a system that is described as a Y of t should represent the value that is currently reached by the system at the given point of time. So using our example, we can say that if the temperature equals 26, then the sensor will return the 26 degrees. There is also error level, E of t, that is calculated using the previously explained feedback loop. It represents the difference between the value that the system is reaching and the current value. So it's easy to calculate in this example, as we only have to minus 21 from 26, which equals 5. There is also a signal that is coming out of the PID controller, U of t, and this signal is called a steering signal. So this is the one that directly interacts with the process. In the AC example, the steering signal can be described by the voltage. So here we see that we need to know Kp, Ki, and Kd to change the E of t into the U of t. And just to let you know, if you want to know more about PIDs overall, you can read the article that we've prepared for this conference, and I think that it will be published together with the slides. What is essential, like a conclusion of this slide, is that the quality of a PID-based control system depends, among others, on PID controller settings. So values that are assigned here on this picture to Kp, Ki, and Kd. Now, I will quickly introduce PID tuning methods. So the ways to search for Kp, Ki, and Kd. As you most probably already realized, all of these parameters, they need to be really carefully selected. And as a control theory is a broad topic, for sure I won't be able to cover it completely during this presentation. The shortest conclusion that I can share for now is that the proper setting will give a correct answer, when the wrong setting will lead us to undefined behaviors like destabilization. And in a real world, wrong parameters can lead even to hardware damages or some catastrophic failures, such as fire or even explosion. And I'm not trying to say that wrong PID controller settings for PTP will cause any explosion, but referring to PIDs like overall, maybe to those that are implemented in, for example, the petrol industry. What is interesting, engineers working with the control systems, they usually decide to tune PIDs manually or leave it with standard settings. There was a research, control loop testing, that indicated that 75% of PID-based loops are out of tune. And this can also apply to the Linux PTP implementation as we use default P and I values. And nowadays, we do it. Besides that, nowadays we have many possible tuning rules. And there is a handbook of PI and PID controller tuning rules that presents over 560 tuning rules defined only for PI controllers. But the problem is that the most classical methods require explicit mathematical modeling of the whole process plant. That is, first of all, expensive, as we have to calculate the transfer function that represents the process. And the transfer function itself can change over the hardware lifespan, so the whole process has to be repeated. An alternative to that is to tune a PID controller using the genetic algorithms. So a genetic algorithm is more like a random search method. It mimics the natural evolution process, and it has shown to be capable of locating high-performance areas in complex domains. What is essential, genetic algorithm depends entirely on response from the environment. And to reach the best solution, they use the evolution operators such as reproduction, crossover, mutation, mimicking the process of natural evolution. It will be easier to explain genetic algorithm using a block diagram, so let's take a look at it now. As you can see, the whole procedure starts with a randomly generated group of possible solutions, which is called a population. And the population consists of creatures. Every creature is evaluated using the objective function that Milena will cover soon. An objective function assigns each individual a corresponding number that we call its fitness. The best creature is selected from the population to create a new population. And in the next step, creatures are crossed, mutations introduced. The main goal of mutation is to increase the population diversity and ensure that the entire problem space is solved. In the next step, the generation limit is checked. If the maximum number of generation is not reached, a new generation replaces new one, and the process is repeated. If yes, if it's true, then whole process stops.
So one of the crucial steps in our algorithm is data evolution. We receive values from the genetic algorithm, and we need to find a way to judge them. Provided that we have a set of expected values and a set of observations, error can be defined as a difference between them. General model performance is based on the sum of these errors. Math, and more precisely statistics, offers several metrics which can be used for data evaluation purposes. Each of these metrics has been focused on different data features. Some of them might indicate an error with a greater influence on the final result. Some might indicate model bias rather than error magnitude. In general, average model error can be represented by this formula. I don't want to go deep into math, but just to give you a short overview, I would like to explain some details. First of all, sigma is greater or equal to 1. In our work, we used various methods where sigma is equal to 1 and equals 2. Next variable is wi, which is the scalar weight assigned to each error according to its impact on the entire error. In our case, it's been assumed that wi is equal to 1, because each error should affect model performance in exactly the same proportion. When sigma is equal to 2, then we obtain root mean square error. This is an example of the sensitive metric where bigger errors have more significant impact on the final model performance. Calculation of RMSE is pretty simple and consists of 3 parts. The first part is summing individual errors, what creates total square error. Subsequently, total square error is divided by number of data points, what is equal to MSE, mean square error. The last step is taking RMSE as a square root of MSE. On this slide, we present mean absolute error, where sigma is equal to 1. As you can see, calculation of MAE consists of two parts. The first is obtaining a sum of absolute values of errors, then the result is divided by n. The most important fact I would like to highlight here is that our data are evaluated by calculating the sum of errors at each step. It lets us choose the best creatures for replication in genetic algorithm and compare our approach with existing solution.
So now we can quickly talk about the framework that we created. First of all, I'd like you to know that the framework that we've created is highly flexible and it accepts many parameters. Everything is described in the article that we've prepared for the conference and in the help in the source code. The whole procedure starts with a randomly generated group of creatures that is called a population. Initial group size is one of the parameters, so there is an argument that determines it. Each creature is described by two values, kp and ki. Argument control the maximal value of randomly generated kp, and the other argument can also control the maximal value of ki for each creature. What is important, the minimal value always equals 0. Every creature in the population has to be evaluated. So the creature evaluation process starts with a PI controller parameters change to the values that describe a given creature. And in the next step, the PHC2sys test is executed on the interface. And in the following slides, Maciej will share more details of these steps. As a result of this operation, the creature fitness value is calculated. In the next steps, the best creatures are selected from the population to create a two-linear generation. When the new generation is created, the mutation and crossover operators are introduced. The whole procedure repeats until the limit of the epochs, that is one, again, of the parameters is reached. A crossover and mutation introduce a high probability of losing the optimal solution. It means that there is no guarantee that the fittest creature will be saved for a next generation. And to avoid this, we decided to introduce the elitists. It means that the number of the best individuals from a population is saved before any of these operations takes place. So when a new population is formed, our framework examines to see if there are any better results than the previous that he was storing, and updates its content accordingly.
So the primary goal of our algorithm is to make our follower system's time match to the leader time as closely as possible. That's why we tune PI parameters to minimize the leader offset. In an ideal situation, the offset between the leader and our system tune is equal to 0. As I mentioned before, evaluation procedure is needed to calculate the difference between expected and observed values. The framework gives a possibility to choose metrics and compare their results. We can select between 3, which are the most accurate from the statistical point of view: MSE, RMSE, and MAE. Additionally, we would like to make sure that values returned from genetic algorithm reach better results than default values of Kp and Ki, which are equal to 0.7 and 0.3 respectively. To compare performance, we also used an evaluation process.
Okay, so we started the POC with the PHC2sys tool. So at the beginning of each run, we set a fixed initial offset between the device under test and the system time, so that all runs have the same starting conditions. Then we started the tool, the PHC2sys, to synchronize the time. We used 20 reads per each correction to minimize the impact of past contention. Used obviously the different P and I parameters that a given creature had, and then run the tool for a fixed time. So at the beginning, we started with the short runs that allowed us to have a reasonably short total test time while maintaining a reasonable quality of the results. And after that, we ran the long runs, which took 5 minutes per each creature. And in the end, the script parsed the output of the PHC2Sys tool, calculated the fitness score using one of the metrics that Milena introduced before, and generated the graphs.
Okay, so let's talk about our results. Test was repeated for 3 metrics listed on the slide, and for the 3 different number of epochs. The first step of result analysis is choosing the lowest error calculated for a specific creature in each epoch. So a set of errors is created. Then the lowest value from a series is taken and compared with values generated using default KP and KI. In this table at the top, you can see the errors comparison and the final improvement. The 2 first parameters are KP and KI. Elite KP and KI are generated by a genetic algorithm in 10 epochs. The initial population was 8, time of a single test was 80 seconds. The third parameter is the result calculated using MSE. General improvement in this case is equal to 32%. And the same results are presented graphically. On the top, you can see how the offset changed over time. The bottom graph histogram shows the normalized frequency of specific values. We have less fluctuation on the right side. Moreover, we can observe that more values are equal to 0, which is closer to an IDA model. It proves that the genetic algorithm successfully optimized parameters of the PI controller used by Linux PTP to even out timing errors. Similar graphs were created for each metric. In case of RMSE, the fluctuation is also smaller than in case of default values, and the improvement here is 23%. Here we have a graph dedicated to MIAE. All of them shows that frequency has been adjusted. Considering that the quality of the systems that are based on PID controllers depends, among others, on PID controller settings, genetic algorithm turned out to be an effective automated methodology of tuning PI.
Yeah, we also run the test in the long runs, the 5 minutes per test, and we use the MSE metric to score them. And in this experiment, we wanted to see how fast will we get a good result, or the one that will be close to the best one that we achieved in the run. And as you can see, we actually got very good results even in the first try. The very first run was the one that used the default values, and in the second run that we had, actually we got very good results, and in the third one we already got very close to the best of all of those, which was reached at generation number 14. And as you can also see, that due to the random nature of genetic algorithms, the future mutations yield random results. So some of the elite fitness per each generation was worse than previous ones. But then overall, we actually selected the best one of all of them. And if it comes to the future work that we plan to do, the first thing that we would like to have is the coarse validation of stability of input parameters, because we actually found some mathematical models that we want to use, and we want to remove the configurations that are known to be unstable and replace that with a different creature to actually get better overall results. Then we will rerun the same framework using the PTP4L, do longer test runs, and try to find optimal number of epochs, because we, as we've seen on the previous slide, even in like 3 epochs were enough, but we want to look closer at how many do we need. And also we want to find an optimal elite size to make sure that we pick the right number of best results to use for generating next creatures and next generations.
So now it's time to really quickly wrap up the presentation. First of all, I'd like you all to remember that PTP is crucial to meet the strict telco requirements that were introduced by 5G and LTE implementations. And Linux PTP uses PI controller, which is a specific case of PID controller, and it is used there to minimize the errors and as a side effect, improve the synchronization quality. The other thing is that among other possible PID tuning methods, a genetic algorithm can be used to find the proper settings. And this is what we did in our framework. Our framework also allows users to use different metrics that allow to optimize different goals. And using this methodology, we've reached up to 32% smaller errors comparing to the default settings. And now we're done, and it's a time for a Q&A.
All right. Thanks for the applause.
Thank you.
And now we're going to open it up for the Q&A. All right, maybe we'll wait. Maciej, should we wait for the applause? There's a lot.
Keep it going. Keep it going.
Don't want to encourage this. Don't want to encourage this. Okay, guys, come on. So this Q&A, I don't know if PJ, do you want to come on stage, or I can show your question on the stage here, and then if you want to come on stage, I can bring you up as well. Maybe you have a follow-up or something. All right, so that's the question.
Okay, yeah, so PID controller is a generic term, so we can't really change it, but fortunately PTP4L uses the PI controller, so I hope this won't create any more confusion.
Okay, let's hear from PJ.
Actually, that pretty much answers the question. When I saw that, I was like, "Oh, you're gonna stitch this into the namespace framework," and then I was like, "Nope, that's not the case." So, yeah, I'd just be very careful to annotate that with our sea of different terms for things that are potentially very related. That can be pretty confusing. So, but
yep,
thanks.
true. Thanks.
All right. Okay. So next is a question from. Okay, PJ answered. Srijit. Okay, I'll put it on stage. And Srijit, if you want to go on stage, just raise your hand and I'll bring you in. So there's a question.
Okay. Yeah, so how the framework works. Basically, the PHC2sys is actually trying to minimize the offset between the system time and the PTP time taken from the PHC inside the NIC. There is no really digital to analog error, but although, yeah, maybe, well, it depends how you look at it. But generally, yes, we are in most cases ignoring the initial stage. Actually, our framework skipped past the initial state because it's basically usually just a big jump of time in value, and that's it. And then we actually focused on the part that is when the state is basically more or less stable. and we are still constantly synchronizing time between our NIC and the system time. We wanted to get the lowest error possible that we could, which means we wanted to prevent the controller from oversteering it too much and generating, for example, unacceptable differences like, a couple hundred nanoseconds just before the controller is because the controller is out of tune.
Okay, Shriyat, if you have a follow-up, just raise your hand and I'll bring you on. And I'm going to mark this as answered unless he comes back again. Next question is from Pedro. I'm going to show it on the stage here. And Pedro, if you want to go on stage, just raise your hand. I'll bring you in.
Marta, you want to take that one? We can't hear you. Okay, I think Marta may have some difficulties. But yeah. Basically, we have not really considered any other approaches initially. We went straight to genetic algorithms because Marta had some experience with them. So we wanted to, trial by fire and just first check whether this approach will work or not. And then maybe, try to find something else. So for this moment, we only use genetic algorithms.
Okay, are there any more questions? Marta, do you want to add? Is your mic working now?
Yeah, you're still muted in the tool,
yeah,
so maybe try to.
It shows muted from your side.
Okay, maybe. Yeah, we can't. No, it's not.
We can't hear you.
Yeah, we can't hear you.
Yeah,
unfortunately.
it's all right. Okay. So I'm going to mark that as answered then. Pedro, if you have any other commentary. Right. So next question. Sorry, I think that's it.
Yeah, I see one more question, a new one from Wojtek. Can GA help to eliminate the negative effects of PCIe bus contention? Well, it will be as good as PID controller gets. I would assume it may help because it may pick the parameters that will be slower and will make the PI servo actually pick slower response. So bus contention that's temporary will not impact the result so much. But we haven't tested all those scenarios yet. This is rather a pretty initial stage of this project, so we haven't got too many results. We, as we said in the presentation, we have plans to move on to PTP4L, but we can also try different cases there.
Okay. Any more questions? Wojtek, you're fine with that answer, or you can raise your hand. Okay, there is Marcus answered. There's another question here from. Okay.
Yeah, that's a response.
That's the response. Unfortunately, Srijit is trying to set up the next session, so he's not here to make commentary. I don't know if I can. Okay, so he'll see this in the recording.
Yep.
There is one more question for you here. It's from Pedro again. Says, Sean, is the framework available?
Not yet. We will try to open source it, but this requires some time, so cannot give you dates, but we will try to open it.
Okay. Any other questions, folks? Just post on the Q&A or raise your hand. Any other commentary you wanted to add? Maciej, Milena. I know we can't hear Marta, unfortunately. Any last words?
Yeah, thank you for joining us.
Okay.
Yep.
All right. Thanks, everybody. Let's give them a hand of applause here. And we'll see you on the other side. There's another session that's going to start shortly. But thank you for your presentation and work. We appreciate it. Thanks. And now I'm going to end the session.
Bye.
Bye.